welcome to the next video in this unit on differential equations. In this video, we'll explore several numeric techniques for solving PDEs. In many ways, this marries the numeric linear algebra techniques we discussed in the linear algebra unit with the language of differential operators we've been cultivating in this unit. First, we'll look at different types of discrete derivatives, their error, and how they converge to the analytic solutions. Then we'll explore the pros and cons of a few different methods for solving differential equations, including the Euler Method and the RK4 algorithm. We'll see how each depend on step size and when they converge. We'll start off using the heat equation as an example of techniques used to solve elliptic equations, then touch on methods for hyperbolic PDEs with a wave equation and parabolic PDEs with a Poisson equation. At the end, we'll take a brief look at finite element methods and defining operators on meshes. In this video, we'll be discussing four broad classes of algorithms. Explicit methods, for example, forward Euler. In these methods, we calculate the state of a system at a later time point from the state of the system at the current time point. These are fast but often numerically unstable. Higher order methods, for example, RK4. These involve refining the approximation by taking into account higher order approximations of derivatives. These are more accurate than simple explicit schemes, but suffer from the same numeric instabilities. Implicit methods, for example, backwards Euler. Here we must solve an equation that depends both on the state of the system at the current time and the state of the system at the next time step. These are stable, but often very slow. Mixed methods, also called IMEX methods, for example, the Crank-Nicolson method. These take advantage of the pros and cons of implicit and explicit methods. For example, implicit methods can be used on linear terms and explicit methods can be used on the nonlinear ones. For each of these methods, we'll also discuss their numeric stability. Back when I was first learning calculus, my teacher motivated integrals using Riemann summation. Here we're going back to blending geometry and calculus to derive discrete approximations to differential equations. But instead of starting with the discrete case and building the continuous, we'll start with Taylor expansions and build the discrete derivatives from them. F of x plus a equals f of x plus f prime of x times a plus 1/2 f double prime of x times a squared, and so on through 1 over n factorial times the nth derivative of f of x times a to the n, plus terms of order a to the n plus 1. We'll be using this big O notation for the order of the error in our calculations. For the first derivative, we only need to keep the first two terms of the Taylor expansion. F of x plus a equals f of x plus f prime of x times a plus terms of order a squared, which gives us f prime of x equals f of x plus a minus f of a divided by a plus terms of order a. This is a first order approximation to the first derivative of f at x. You might remember that the analytic definition of derivative is this formula in the limit that a goes to 0. However, this isn't necessarily the most symmetric version of this discrete first derivative. Another definition uses the difference between f evaluated at x plus a and f evaluated at x minus a. F of x plus a minus f of x minus a equals 2a times f prime of x plus terms of order a cubed. The centered difference formula, f prime of x equals 1 over 2a times f of x plus a minus f of x minus a plus terms of order a squared, is a second order approximation to the first derivative. This is important because as we integrate, we might be taking steps in either direction towards a or minus a, so having a biased derivative can accumulate more error. Similarly, the discrete second derivative is defined from the sum of the same two terms. For this approximation, we'll be keeping the Taylor series to second order. F of x plus a plus f of x minus a equals 2 times f of x plus f double prime of x times a squared plus terms of order a to the fourth. So the discrete second derivative is given by f double prime of x equals 1 over a squared times f of x plus a minus 2 f of x plus f of x minus a plus terms of order a squared. This formula is implicitly symmetric. You'll note that the error depends not only on the choice of discrete derivative, but also on a, which is the size of the step we're taking. It may appear that one choice of derivative is better than the others. However, the way they are implemented in different numerical schemes can affect the stability of their integration. Before we get to discussing different algorithms, we need to discuss how to set up our problem and what kind of information we'll need to keep track of. In most problems we'll explore, we'll set up a discrete set of values for each independent variable. This rectangular mesh is the domain for our discrete system. For instance, if we're solving a partial differential equation in two variables x and t, such as the heat equation, ut equals k uxx, we'll have a mesh consisting of equally spaced spatial values and equally spaced temporal values. Each discrete derivative we take will be sums and differences of the values of neighboring sites on this mesh. If we have values of our function u of x and t in the domain x goes from 0 to L and t is greater than 0, then we can split our mesh into n units in the x direction and j units in the t direction. The nodes are labeled ti and xm. Our discrete derivatives are defined on the lattice sites u of ti and xm is uim. With step size delta x equals xm plus 1 minus xm equals L divided by n for the spatial direction, and delta t equals t plus 1 minus ti for the time direction. Instead of keeping track of partial derivatives explicitly, we'll keep track of the value of our function u on different lattice sites. Approximations of derivatives are then linear combinations of the values uim. We'll use the heat equation dTu equals dxxu with boundary conditions u of 0 and t equals alpha of t and u of 1 and t equals beta of t, and initial condition u of x and 0 equals u naught of x as a toy model to illustrate most of the methods we're about to discuss. The generalization of these techniques works for parabolic differential equations. We'll start with explicit methods, an example of which is the forward Euler method. Here we'll use the forward difference at time ti to calculate the time derivative. dTu equals ui plus 1m minus uim divided by delta t, and a second order central difference for the spatial derivative. dxxu equals uim plus 1 minus 2uim plus uim minus 1 divided by delta x squared. Thus we can explicitly obtain the value for ui plus 1m at time ti plus 1. ui plus 1m equals 1 minus 2r times uim plus r times uim plus 1 plus uim minus 1, where r equals delta t divided by delta x squared. This is a stencil that illustrates the nodes needed to calculate each discrete step. Since the time derivative has error of order delta t, but the spatial derivative has error of order delta x squared, the time step has to be much smaller than the spatial step in order for the time error not to overwhelm the calculation. We can write this as a matrix equation for the I plus 1th iteration. The state of the system at time ti is given by the vector ui equals the transpose of ui1, ui2, etc. through uin minus 1. Note that the value of the boundary nodes ui0 and uin are set by the boundary conditions. We could rewrite the update equation as ui plus 1 equals mui plus bi, where m is an n minus 1 by n minus 1 tridiagonal matrix with values 1 minus 2r along the diagonal and r on the off-diagonal elements. And bi is a vector of length n minus 1, which equals r alpha I, 0, 0, etc. through r beta I is the vector of boundary conditions at time ti. This equation updates the interior nodes of U. When we talked about iterative methods for solving eigenvalue problems, we discussed that such systems converge only when the spectral radius, or the absolute value of the largest eigenvalue of the matrix, is less than or equal to 1. The same applies here, since each time step is an iteration of the same system. Our example converges when 1/2 delta t divided by delta x squared is less than or equal to 1. For example, here is a system with delta x equals 0.1. We'll look at the solution for 3 values of delta t. The first is delta t equals 0.001. This converges nicely. The second is delta t equals delta x squared over 2, which equals 0.005. This converges, but you can see there are a lot of oscillatory fluctuations as it settles down. The third is delta t equals 0.01. The fluctuations we saw in the last system grow until the values don't even fit on the plot anymore. Since there are values for delta x and for delta t for which this integration scheme converges, it is called conditionally stable. The first order integration step we just did has errors that compound over the whole integration. Higher order algorithms can minimize this error by taking higher order approximations of derivatives across the interval between t and t plus delta t. One of the most frequently used algorithms for solving initial value problems is the fourth order Runge-Kutta method, also known as RK4. Forward Euler is a first-order Runge-Kutta method that is an implementation of Riemann summation. RK4 is an implementation of Simpson's rule, integrating a cubic approximation of the curve at each time interval. Consider an initial value problem of the form y prime of t equals f of t and y with initial condition y of t naught equals y naught. Again, we'll divide our domain into regions of size delta t. This method uses a midpoint t plus delta t over 2 to cancel out the error from the lower order approximations. This algorithm uses a weighted average of 4 slopes in the interval to calculate a much more refined update. First, we'll estimate the derivative at ti. Yi prime equals f of ti and yi, which equals our first slope, k1. Then we'll use this to estimate the function at ti plus a half. Yi plus a half equals yi plus delta t on 2 times f of ti and yi, which equals yi plus delta t on 2 times k1. Next, we want to estimate the slope at ti plus a half using k1. Yi plus a half prime equals f of ti plus delta t on 2, and yi plus delta t on 2 k1 equals our second slope, k2. From this, we get another estimate for yi plus a half using k2. Yi plus a half equals yi plus delta t on 2 times f of ti plus delta t on 2, and yi plus delta t on 2 k2 equals yi plus delta t on 2 times our third slope, k3. Then we can approximate the function at yi plus 1 using k3. Yi plus 1 equals yi plus delta t times f of ti plus delta t, and yi plus delta t k3, which equals yi plus delta t times the fourth slope, k4. Combining these together and averaging over all the slopes, the update step is yi plus 1 equals yi plus 1/6 times delta t times k1 plus 2k2 plus 2k3 plus k4. This approximation has error of order delta t to the fourth. For the same step size, this method will be much closer to the exact solution than the forward Euler method. This shows a comparison of the forward Euler and RK4 with the same step size, along with the exact solution. Since this implementation is still explicit, implementing it for PDEs can still suffer the same instabilities as other explicit methods. Implicit methods, such as the backwards Euler method, don't have the same time-step constraints that the forward Euler method or other explicit methods have. Imagine we have a differential equation of the form ut equals f of u. We can calculate the backwards difference formula for the first derivative. dtu equals uim minus ui minus 1m divided by delta t, plus terms of order delta t squared, equals f of ui. We replace I with I plus 1 in the backward Euler method, so instead of integrating forward like we did before, we now have an implicit equation to solve for ui plus 1 at each time step. For our example with the heat equation, this is a linear equation. ui plus 1m minus uim over delta t equals ui plus 1m plus 1 minus 2ui plus 1m plus ui plus 1m minus 1 over delta x squared, or 1 minus 2r times ui plus 1m minus r times ui plus 1m plus 1 plus ui plus 1m minus 1 equals uim. The stencil for this takes the values at I plus 1 and uses them to calculate the value at I. In matrix form, this can be written as m tilde times ui plus 1 equals ui plus bi plus 1, where m tilde is the same matrix M as we calculated before, except r has been replaced by minus r. This amounts to solving an algebraic equation for each time step. The stability analysis here says that the spectral radius of m tilde inverse given by the absolute value of lambda naught equals 1 over 1 plus 2r is less than or equal to 1. Since r is greater than 0 by definition, this condition is always satisfied. Therefore, we call this an unconditionally stable method. This is the same equation we just solved using the forward Euler method. Note that for the largest step size, delta t equals 0.01, this converges almost immediately to the solution. Here I've chosen a much smaller time step, delta t equals 0.001, to show its evolution. The error for the heat equation grows linearly with time step size and quadratically with spatial step size. The main downside of this method is that calculating the solution to the auxiliary equation at each step can be very time-intensive, particularly for nonlinear equations. A fourth type of algorithm, the IMEX method, blends implicit and explicit methods. These methods often use a central difference for the time step at ti plus a half rather than a forward derivative at ti or a backward derivative at ti plus 1. We'll illustrate this with the Crank-Nicolson method. ui plus 1m minus uim equals r on 2 times ui plus 1m plus 1 minus 2ui plus 1m plus ui plus 1m minus 1 plus uim plus 1 minus 2uim plus uim minus 1. Here, the stencil uses spatial derivatives at both time ti and ti plus 1 to approximate the update. In matrix form, this is p tilde ui plus 1 equals p ui plus 1 half bi plus bi plus 1. Here, p tilde is a tridiagonal matrix with diagonal entries 1 plus r and off-diagonal entries minus r over 2. Likewise, p is the same as p tilde, but with r goes to minus r. The b vectors are the boundary conditions at times ti and ti plus 1. Here the convergence depends on the spectral radius of p tilde inverse p, where lambda naught equals 2 minus r over 2 plus r. Again, the absolute value of lambda naught is always less than or equal to 1, so this method is unconditionally stable. Here is our toy problem solved using the Crank-Nicolson method. So far, all the methods we've looked at are designed to solve PDEs that are first order in the time derivative. Now we'll spend a little time talking about equations that are second order in time, such as the wave equation. This method works for general hyperbolic equations. Here we'll solve the wave equation utt equals uxx with boundary conditions u of t and 0 equals alpha of t and u of t and l equals beta of t, and initial conditions u of 0 and x equals f of x and dt u of 0 and x equals g of x. We'll use the centered finite difference for both second derivatives. dt squared uim equals ui plus 1m minus 2uim plus ui minus 1m divided by delta t squared, plus terms of order delta t squared. And dx squared uim equals uim plus 1 minus 2uim plus uim minus 1 divided by delta x squared, plus terms of order delta x squared. Then our iterative update step is ui plus 1m equals s times uim plus 1 plus 2 times 1 minus s times uim plus s times uim minus 1 minus ui minus 1m, where s equals delta t divided by delta x squared. This is the stencil for the discrete wave equation. In matrix form, we have ui plus 1 equals qui minus ui minus 1 plus bi, where Q is a tridiagonal matrix with diagonal entries 2 times 1 minus s and off-diagonal entries s. Bi is the vector of boundary conditions at time I. You'll notice that the update step ui plus 1 depends both on the current step ui and the previous step ui minus 1. This poses a problem for the first step. For the first step, we can use the initial condition dtu of 0 and x equals g of x to approximate the previous step ui minus 1 equals ui minus delta t times ui prime plus terms of order delta t squared. u1m equals s times u0m plus 1 plus 2 times 1 minus s times u0m plus s times u0m minus 1 plus gm times delta t. Or in matrix form, u1 equals 1 half q u0 plus g times delta t plus 1 half b0. Since this is an explicit method, the algorithm converges when the absolute value of lambda naught, which equals 2 times 1 minus s, is less than or equal to 1. Here is a solution to the wave equation with time step equals spatial step equals 0.01. For 2D equations, we have to work out a more complicated spatial derivative. For a rectangular domain where the mesh size is the same in both directions, delta x equals delta y equals delta, the discrete approximation of the Laplacian is given by dxx umn plus dyyy umn, which equals 1 over delta squared times um plus 1n minus 2umn plus minus 1n plus 1 over delta squared times umn plus 1 minus 2umn plus umn minus 1 plus terms of order delta squared. This can be simplified to 1 over delta squared times plus 1n plus umn plus 1 minus 4umn plus minus 1n plus umn minus 1. This is the stencil for the 2D Laplacian. Imagine we're trying to solve the Poisson equation. The Laplacian of u of x and y equals f of x and y with boundary conditions u of 0 and y equals g1 of y, u of L and y equals g2 of y, u of x and 0 equals h1 of x, and u of x and w equals h2 of x. our discretization divided the x direction into m units with m plus 1 nodes, and the y direction into n units with n plus 1 nodes. The state of our system at any given time is represented by the flattened vector u equals the transpose of u00, u10 through um0, u01, u11 through um1 through umn. However, we really only need to consider updating the interior nodes since the boundary nodes are specified by the boundary conditions. Then in matrix form, the equation we want to solve is AU equals B, where A is a block tridiagonal m-1 times n-1 by m-1 times n-1 matrix. The off-diagonal elements are given by minus the m-1 by m-1 identity matrix I, and the diagonal elements are given by D, which is a tridiagonal m-1 by n-1 matrix with diagonal elements 4 and off-diagonal elements -1. The vector B is the sum of the vectors f, which is the discretization of the inhomogeneous term in the Poisson equation. F equals the transpose of f11, f21 through fm-11, f12, f22 through fm-12, etc. through fm-1, n-1, and the vector of boundary conditions. Imagine we have a 5x5 grid. The 9 interior nodes are given by u equals the transpose of u11, u21, u31, u12, u22, u32, u13, u23, u33. Our block tridiagonal matrix A is split into 9 blocks, each containing a 3x3 matrix. The 1st, 5th, and 9th are given by 4 minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 4. The 2nd, 4th, 6th, and 8th are given by minus the identity, minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. The B vector is given by minus delta squared f11 plus u01 plus u10, minus delta squared f21 plus u20, minus delta squared f31 plus u41 plus u30, minus delta squared f12 plus u02, minus delta squared f22, minus delta squared f32 plus u42, minus delta squared f13 plus u03 plus u14, minus delta squared f23 plus u24, minus delta squared f33 plus u43 plus u34. We can solve this using any technique that we'd like to invert A. However, since A is a block tridiagonal matrix, there are much faster methods than Gauss-Jordan to invert it. Here is an example of the Poisson equation being solved on more and more refined meshes. Lastly, we'll take a few moments to discuss the finite element method. This won't be a complete treatment by any means, but hopefully it gives you an idea of what the finite element method is and when you can use it. This method is primarily used for solving 2D and 3D boundary value problems. Here, the mesh we solve the PDE on is no longer a rectangular mesh, but it's a discretization of space, usually a triangulation, that captures the geometry of the domain. These are used all the time for elasticity simulations and have the advantage that the boundary conditions can be very complex. We need to keep track of each node in the mesh as well as which nodes it's connected to in order to take discrete derivatives on it. Each face in the triangulation is a piecewise linear domain where we must solve a discrete version of our PDE. As with other methods, this often ends up being a set of algebraic equations. If there are dynamics in the system, then the temporal evolution can be solved using a technique such as forward Euler or RK4. In this setup, we need to keep track of the geometry of the mesh throughout the dynamics. Unlike the rectangular mesh setup, our mesh can, and often must, deform as the body itself deforms. The idea behind the finite element method is that as you make the triangulation increasingly refined, the discrete solution will converge to the analytic one. Unlike other methods, the finite element method supports spatially varying material properties, such as elastic modulus or diffusivity. Thank you for watching, and I'll see you next time.